From the dawn of time we have looked beyond, wondering, dreaming of what lay outside our grasp. We grew across vast landscapes and took one small step, first to the moon, then we looked to Mars. We built a space station, but still we wondered what lay beyond. Now it's time for a courageous group of men and women, led by the best of the best that mankind has to offer. We now seek to take that one small step and turn it into one giant leap. We are ready to take on new challenges as our quest to the outer reaches of space continues. What answers will we find on our quest? Our quest to discover the galaxy.
Hi everyone, and welcome to this special Origins edition of Discover the Galaxy. I'm your host, Jason Ross. On this week's program, we're going to start out by looking at the origin of the universe itself, beginning with our own sun and what happens on its surface. Obviously that has a big impact on how we live our lives here on Earth, and we're going to look at how we've come to control as best we can the elements of fire, wind and water. In the second part of the program, we're going to look at the origin of mankind's Apollo missions to the moon. Do you know we're coming up on 50 years almost of our first forays to the moon and back? Then in the final part of the program, we're going to look at the moon's surface itself. Can you imagine what the moon looked like 100 million years ago? Do you know how the craters formed on its surface and when that happened? Well, on our program tonight, we're going to look at how the moon came to be as important to us as it is, and also how it came to be formed the way that it is today. So together, let's take a seat back, have a look, and together discover the galaxy.
The observable universe is about 46 billion light years in radius. Scientific observation of the origins of the universe has led to what we all know as the Big Bang Theory. The Big Bang Theory is the prevailing cosmological model that describes the early development of the universe, which is calculated to have begun some 14 billion years ago. Observations of various supernovae have shown that the universe is actually expanding at an accelerating rate. There are many competing theories, however, about the ultimate long-term fate of the universe. Many physicists believe that, if anything, preceding the Big Bang is hard to work out, speculate, or come up with any answers at any time in the future. There are many discussions about multiverses, a hypothesis that suggests that our universe might be just one of an infinite number of universes that exist simultaneously. Of course, the Sun is the star at the centre of our own solar system. It is almost perfectly spherical and consists of hot plasma woven between magnetic fields. In case you're wondering, the Sun is about 1.4 million kilometres in diameter and around 109 times the size of Earth. It weighs a gigantic 330,000 times our own Earth's mass and accounts for about 99.86% of the total mass of our entire solar system. Our own Sun formed some 4.567 billion years ago after the gravitational collapse of a region within a large molecular cloud. Most of that matter gathered in the centre was formed together, and that orbital disk became our solar system. The central mass became increasingly hot and dense, eventually resulting in thermonuclear fusion at its core that created the Sun that we know today. Our understanding of the universe itself is predominantly based on Albert Einstein's theory of relativity. Now, it's too complicated to get into really with you, but what it outlines is a set of 10 equations that define the distribution of mass, energy and momentum throughout the universe. Because these are unknown in exact detail, cosmological models have been based on a principle that states that the universe is both homogeneous and isotropic. What this really means is that they assert that the gravitational effects of the various galaxies affect fine dust and the planets around them. The assumption of a uniform dust makes it easy to solve Einstein's field equations and predict the future and the past expansion of the universe on a cosmological timescale. The universe itself is composed of only 5% of matter, including atoms, stars and galaxies. The universe consists of 25% of dark matter, which is a hypothetical particle that has not even been detected. And dark energy accounts for some 70% of the universe, which is a kind of energy density that exists in empty space. Of course, all this information sounds wonderful, but as you know, as scientific advancements continue on, we learn new things and discover previous theories were incorrect. So what we learn in the future about our planet, our role in the solar system, the Sun and the galaxy itself is anyone's guess, but only through scientific research and knowledge can we together discover more about our galaxy. Welcome back. In our second part of this Origin special, we're going to take a look at mankind's origins of our missions to get to the moon and back. Do you know that we're coming up on almost the 50th anniversary of the original Apollo missions that set us down on the surface of the moon? You know, Neil Armstrong said that standing on the moon wasn't the most dramatic thing he'd ever experienced. In fact, it was looking back at the Earth and seeing this beautiful bright blue object in the middle of abject darkness in the middle of the universe, and that's what made the whole experience incredible. So let's take a look at the early Apollo missions and what was involved that got us to the moon and let us take that one final step for mankind.
45 years ago, Apollo Apollo 8 astronauts Frank Borman, Jim Lovell, and Bill Anders became the first humans to orbit the Moon and the first to witness the magnificent sight called Earthrise. Now, for the first time, we can see this historic event exactly as the astronauts saw it, thanks to new data from NASA's Lunar Reconnaissance Orbiter, or LRO. LRO's superb global lunar maps, combined with the astronauts' own photographs, reveal where Apollo 8 was over the Moon, and even its precise orientation in space when the astronauts first saw the Earth rising above the Moon's barren horizon.
These are the scale sizes of the Earth and Moon. The radius of the Moon is 3.7 times less than that of the Earth. Its mass 81 less. If we observe the translational motion of the Moon from the north side of the solar system, the Moon rotates counterclockwise around the Earth. For each complete revolution of the Moon around the Earth has rotated on itself more than 27 times. The Moon takes to go 360 degrees around its orbit 27 days, 7 hours and 43 minutes. This cycle is called the sidereal month. If we starting a movement in which the Sun, Moon and Earth are aligned, we consider a complete cycle of the phases of the Moon. When once started the movement, the three bodies retake its start position. Lunar and solar eclipses can occur when the nodes align with the Sun, roughly every 173.3 days. The eclipse occurs when the Moon falls on a node aligned between Earth and Sun. In any other position of the nodes, eclipses will not occur, because the Moon would never be aligned between the Sun and the Earth, even though the Moon is in the middle of both bodies, as the Moon does not coincide with the plane of the ecliptic. The translational and rotational periods of the Moon are the same. Moon therefore always offers the same hemisphere to an observer on Earth. This hemisphere is called the near side of the Moon. The opposite hemisphere will always be hidden to an observer on Earth. It is called the far side of the Moon. The far side of the Moon was first perceived by humans through the Soviet probe Luna 3. The Soviet spacecraft photographed the far side of the Moon on October 7, 1959. Five decades later, we know in detail the map of the far side of the Moon through the Grail mission by NASA. Begins the first quarter, during which the Moon is growing. If we observe the crescent from the North Pole, the Moon takes the form of D. However, if we go to the South Pole, the Moon takes the form of C. If at that moment one views it from the line of Ecuador at the night, the Moon will appear to us in the form of U. Between 14th and 15th day, the full moon appears. The Sun illuminates the whole near face of the Moon. From the South Pole we'll see a full moon reversed from how we've seen from the North Pole. The Sea of Tranquility and all other seas are presented flipped 180 degrees. At the midnight in equator, the full moon will be located at the zenith. If the observer looks up and turns upon himself, may see the Moon in any position. During the full moon the Earth is between the Sun and the Moon. If the right conditions are met, can occur lunar eclipse. This phenomenon occurs when the shadow of the Earth darkens the surface of the Moon. This eclipse can last several hours. During the third quarter the Moon begins to wane. View from the North Pole, the waning Moon will take form of C. Viewed from South Pole it will take the form of a D. At the night from equator, the waning moon is seen in the form of U. From the northern hemisphere, the waning moon will take a form between C and U. The trend one form or another will depend on the latitude and time of year in which we find ourselves. At a latitude between 40 and 50 degrees north, the waning moon will take the following form seen in the night by an observer who is between these latitudes. These are latitudes corresponding to most of the European countries, northern United States, North Korea and northern Japan. In the southern hemisphere at a latitude of between 10 to 30 degrees we see this other waning moon. This latitude corresponds to much of the South American countries in southern Africa, and northern and central Australia. The shape of the waning moon is between a D and a U, with a tendency toward a U, because we are not far from Ecuador. Ended our journey in the last quarter waning. End the cycle giving way to the new moon again.
For the astronauts, seeing the Earthrise was an unexpected and electrifying experience. And one of the 3 photographs taken by Bill Anders became an iconic image of the 20th century. But as we've just seen and heard, that photograph was actually a group effort. Not just because Jim Lovell found the roll of color film and gave it to Anders, but because the astronauts wouldn't have seen the Earth if Frank Borman hadn't been turning the spacecraft just as it was coming up. Today, the Earthrise has become a symbol of one of history's greatest explorations, when humans first journeyed to another world and then, looking back, saw their home planet, in Lovell's words, as a grand oasis in the vastness of space.
Hi and welcome back. In our final part of the program on Discover the Galaxy, we're going to take a look at the origin of the Moon itself. How did it come to be in our orbit? When did it get impacted by all those asteroids that formed the craters on the surface? And what role does the Moon play to all of us here on Earth? So let's take a look at its history and discover the galaxy, and more importantly, discover our own backyard by looking at the origin of the Moon. The Moon is the Earth's only natural satellite, and while not the largest natural satellite in our solar system, it is the largest relative to the size of the object it orbits, namely Earth. After that, Jupiter's satellite Io is the second most dense satellite amongst those we know. The Moon is thought to have formed some 4.5 billion years ago, not long after Earth. Although there are several hypotheses for its origin, the most commonly accepted explanation is that the Moon formed from the debris left over from a giant impact between Earth and a Mars-sized body. The Moon is exceptionally large relative to Earth, a quarter of the diameter of the planet and 1/81th of its mass. It is the largest moon in the solar system, as I said, relative to the size of the planet that it orbits. The Moon makes a complete orbit around Earth with respects to the fixed stars every 27.3 days. But because the Earth is moving in an orbit around the Sun at the same time, it takes slightly longer for the Moon to show the same phase to Earth, which is about 29.5 days, a month. The tides on Earth are mostly generated by the gradient in the intensity of the Moon's gravitational pull from one side of the Earth and the tidal forces. Because Earth spins about 27 times faster than the Moon around it, the bulges are dragged along with Earth's surface faster than the Moon in fact moves itself, rotating around Earth once a day as it spins on its axis. Thus the ocean tides are magnified by other effects, including Earth's rotation through the ocean floors. The gravitational attraction of the Sun on Earth's oceans is almost half that of the Moon.
We've lived on the Earth for a long time, and we've gotten pretty good at it. In fact, we've gotten so good at it that we've started thinking about living somewhere else. Somewhere like another planet, or even somewhere as close as our moon. Now, one of the reasons we're so good at living on the Earth is that it has pretty much everything we need. Somewhere like the moon doesn't. So if we want to live on the moon, we're going to need to take a few things with us. And what are the 3 basic things we need in order to live? That's right, food, water, and air. Let's start with air. The moon has none. Humans need a combination of gases in order to breathe like we do here on Earth. So what happens when we start running out? We can bring more, but that gets expensive. So we need to find a way to make some more on our own. How about adding some plants? Plants take our carbon dioxide and convert it into oxygen. And as a convenient byproduct, we can eat them too. That helps solve our food problem. But we're forgetting one thing. Both humans and plants need water. We'll bring some to start, and we've come up with some clever ways of recycling it. That can keep us going while we search for water or ice. So we have our food, our water, and air. What else do we need to deal with? That's right, the sun. The sun helps plants grow, and we can use solar panels to give us power. But too much sun can be dangerous. On the Earth, we're protected by our atmosphere, so we get just enough sunlight. But on the moon, there is no atmosphere, so we need to protect ourselves from all that radiation. So now we're living happily on the moon. But what happens when we want to do something like order pizza? Well, on Earth, we just pick up the phone. We can do the same thing on the moon, but it's not that simple. We need satellites to make that call. But seriously, folks, our scientists on the moon will be doing more than just ordering pizza. They'll be sending lots of information back to the Earth, so we can learn more about our new environment. And when it comes to living in space, the more we know, the farther we can go.
Like clockwork, the full moon appears every month in our sky, a sight so familiar that we often take it for granted. But about twice a year, over the course of a few hours, the full moon sports a decidedly different look. What causes this sudden change? A lunar eclipse occurs when the moon passes through the Earth's shadow, just as a solar eclipse occurs when part of the Earth passes through the moon's shadow. But the moon circles the Earth every month as it cycles through its phases, lining up at both full moon and new moon. So why don't eclipses happen twice a month? The reason is that the moon's orbit around the Earth is tilted relative to the Earth's orbit around the sun. Although the Earth and the moon always cast long shadows, they rarely shade each other thanks to the moon's orbital tilt. But if that's the case, why do eclipses happen at all? Throughout the year, the moon's orbital tilt remains fixed with respect to the stars, meaning that it changes with respect to the sun. About twice a year, this puts the moon in just the right position to pass through the Earth's shadow, causing a lunar eclipse. As the moon passes into the central part of the Earth's shadow, called the umbra, it darkens dramatically. Once it's entirely within the umbra, the moon appears a dim red due to sunlight scattered through the Earth's atmosphere. In fact, if you watched the eclipse from the surface of the moon, you'd see the sun set behind the entire Earth, bathing you in a warm red glow. Back home, you'll have to stay up late to watch a lunar eclipse, but if you do, you'll see the moon in rare form, and you'll catch a brief glimpse of our own planet's long shadow.
Unfortunately, that's all the time we have on this special Origins edition of Discover the Galaxy. I hope you've learned a little bit more about how the Sun affects us here on Earth, how we've come to know that the Moon has all these impact craters on it and where they came from during its history, and also you got to learn a little bit about the origins of our own space program with the Apollo missions. From now on, we get to learn where we're going in the future with next week's episode, where we take a look at the weather and the climate patterns here on Earth. But until that time, next week, I hope you've enjoyed the program. I'm Jason Ross. Let's discover the galaxy together, shall we? Bye for now.